Hello students, welcome back to another video of MATHIPHY. In today's video, we will do paper 6, alternate to practical of course code 0625. It's month May, June 2025, a variant 3. Question number 1 says, a student investigates the forces supporting a meter ruler to determine the weight of the meter ruler. He uses the apparatus shown in figure 1.1 and the scale of meter ruler faces upward. Here we have these two stands on which meter ruler is hanging. This force meter is used to measure the weight or the force. Over this side we have the weight of 1.5 Newton, and the student ensures that the meter ruler is horizontal. Briefly describe how to check the meter ruler is horizontal. You may draw a diagram. To check the meter ruler is perfectly horizontal, we will measure the height of meter ruler from the ground at two different positions. Let's suppose here and here. If the height of meter ruler from ground at both positions is equal, then the meter ruler is horizontal. Now I will write all the explanation here as well. Measure height of meter ruler from bench at two different positions. If it is equal, then meter ruler is horizontal. B part says the student adjusts the distance d between the 0 centimeter mark and 1.5 Newton load as shown in figure 1.1. He moves the thread supporting the 1.5 Newton load so that it is at the mark on the meter ruler shown in figure 1.2. So he places the thread holding the load over here, and this is 8 units ahead of 35, so the reading is 35.8 centimeter. Now I will record the distance d, 35.8 centimeter over here as well. Second part says the reading on force meter X is shown in figure 1.3. This is the reading on force meter. Record Fx, the reading on force meter X as shown in figure 1.3. Let me first calculate the value of one small division. For it, I will divide 0.5 with the number of divisions which are inside it, that is 10. So the value of one small division is 0.05. And our force meter is one division ahead of 1.5, so it would be 1.55 newtons. Now C part says the student moves the 1.5 Newton load to the distance d 10 cm, 30 cm, 50 cm, 70 cm and 90 cm. For each distance d, he reads the value Fx on force meter. For distance 10, the force meter is reading 1.17 Newton, and so is the case with all the other distances. Plot a graph of Fx on y-axis and d on x-axis and start from origin and draw the best fit line. So here we have the graph. We have to draw distance on x-axis, and the force on the force meter would be drawn on y-axis. The scale that I have chosen for the table is this. In this scale, on y-axis, my one small box is representing 0.05 Newton of value, and on x-axis, my one small box is representing 2 centimeter of the distance. Now I'll plot all the values from the table in the graph. So here are the plottings. And now I will draw a best fit line, and it will look like this. D part says from your graph determine F naught, the value of Fx when distance is 0 centimeter. So Fx is 1 when the value of D is 0. So the answer is 1 Newton. Next, calculate the weight WR of meter ruler using the equation WR is 2 times of F naught. That means it is 2 times of 1 Newton. So weight of the meter ruler is 2 Newton. E part says state and explain whether your plots made it easy to choose the best fit line. Justify your answer with the reference to your plots. So yes, it was easy to choose the best fit line because you see all the plots are very close to the line, and there is a strong correlation between all the plots and all the values that we have got from the table. So yes, it was easy, and the explanation is because there is a strong correlation between the values. F part says another student does the experiment with the same equipment. He reads the value of fx, which are all higher than the values that we have got in table 1.1. Suggest one reason for this difference. Assume that your values in table 1.1 are accurate. So he might have not set his meter ruler value to 0 before doing the calculations. That's why his answers are getting a bit higher than the original. Question number 2 says a student investigates the cooling of water in a beaker. She uses the apparatus shown. So she has a beaker and a thermometer to measure the temperature. Record the room temperature shown in thermometer in figure 2.1. So the temperature reading is 1 division ahead of 20, so it is 21 degrees Celsius. B part says the student pours hot water into beaker and records the initial temperature theta in table 2.1. She then records the temperature after every 30 seconds and her values are shown in the table. So what she is doing, she filled the beaker with hot water and she records the initial temperature with the help of thermometer, and now she will note the change in temperature after every 30 seconds, and she will record all the readings in the table that is already given by the question. Describe one technique that you use to ensure that the temperature reading in this type of experiment is as accurate as possible. So if you are taking the reading from thermometer, make sure that your eye is at the level of the scale or your eye is perpendicular to the thermometer. So the reason is keep eye perpendicular to the scale while recording temperature to avoid parallax error. Here is the table of the values she has recorded. C part says estimate the temperature at 300 seconds. Use the reading from table 2.1 to guide you. In this table, if you see the temperature change pattern, it is like this. In first 30 seconds, the temperature drop was 2.5 degrees Celsius, then 2, then 1.53 times, then 1 degree Celsius 3 times, and then 0.5. So I assume that after next 30 seconds, the drop would also be 0.5. So the temperature would be 80.5 degrees Celsius. D part says calculate the average cooling rate x1 during the first 90 seconds of the experiment. Use the readings from table 2.1 and the equation. In this equation, T is 90 seconds, theta 0 and theta 90 are the temperatures at T equals to 0 and T equals to 90 seconds. And you have to include the units as well. So let us see what is the temperature at T equals to 0 and T equals to 90 from the table first. At 0 seconds the temperature is 93 and at 90 seconds the temperature is 87. So it would be 93 degrees Celsius minus 87 divided by 90 seconds. And the average cooling rate will turn out to be 0.067, and for the units it would be degrees Celsius per second. Now second part is again same. Calculate the average cooling rate x2 during the middle 90 seconds of the experiment. Use the readings from table 2.1 and the equation given. In this equation again, T is 90 seconds and theta 90 and theta 180 are the temperatures at 90 seconds and at 180 seconds. So at 90 seconds the temperature is 87 and at 180 seconds the temperature is 83. So it would be 87 minus 83 divided by t, which is 90 seconds. And x2, the average cooling rate for the middle 90 seconds, will turn out to be 0.044 degrees Celsius per second. Third part says calculate the average cooling rate x3 during the last 90 seconds of the experiment. Use the readings from table 2.1 and the equation. Over here, theta 180 and 270 are the temperatures at 180 seconds and 270 seconds. At 180 seconds, the temperature is 83, and at 270 seconds, the temperature is 81. So x3 is 83 minus 81 divided by 90 seconds. And the average cooling rate for last 90 seconds is 0.02 degrees Celsius per second. D part says use your results from D to describe the overall pattern of the rate of cooling of water in the experiment. Justify your answer by reference to your results. So if we see the results, x1, which is the average cooling rate for first 90 seconds, is high. Then x2, the average cooling rate for middle 90 seconds, is moderate, lesser than the previous one. And lastly, the cooling rate for the last 90 seconds is dropped, or it's lower than the previous two. So what is the conclusion? That the cooling rate drops as the time goes on. At first 90 seconds it was 0.067, at middle 90 seconds it was 0.044, and at last 90 seconds it is 0.022. Second part says estimate the final temperature of the water after several hours. After several hours, there would be equilibrium reached between the water and the room, and the water would be converted into room temperature. That means its temperature would be 21 degrees Celsius, that is earlier mentioned as room temperature. F part says another student does the same experiment. He starts with the hot water at lower initial temperature. Suggest how his cooling rates are likely to compare with those in B. Use your results to explain your answer. Cooling rate is calculated by initial temperature minus final temperature divided by the time interval. That's mean it depend upon the initial temperature. If initial temperature is high, cooling rate would be high. If initial temperature is lower, cooling rate would be lower. So my suggestion is cooling rate would be lower. And for explanations, we have to use the values from our results. See, when initial temperature is 93, the cooling rate is higher. When initial temperature is 87, the cooling rate has been dropped. So in the explanation, I will write in x1 initial temperature is high, so cooling rate is greater. In x2 the initial temperature is low, so the cooling rate is low. Second part says state one variable other than initial water temperature that the student needs to control. So that is volume of water. Question number 3 says a student investigates circuits containing different combination of resistors. Circuit A is shown in figure 3.1. Circuit A is not complete. In circuit A, we have R1 and R2 resistors connected in parallel, and then Rp resistor connected in series with R1 and R2, and an emitter. A part says on figure 3.1, complete the circuit to show a voltmeter connected to measure the potential difference across the terminals P and Q. To measure the potential difference across the terminal P and Q, we have to connect the voltmeter in parallel, just like this. B part says the student measures the potential difference V across the parallel combination of resistors R1 and R2 and measures the current I in the circuit. His readings are shown in figure 3.2 and figure 3.3. So this is the voltmeter reading and this is the emitter reading. Read and record in the first line of table 3.1 the values of V and I shown on the meters in figure 3.2 and 3.3. So in the voltmeter, the reading would be 0.8 as it is 3 division ahead of 0. So 0.8 volts. For emitter, let us just calculate the value of one small division first. So it would be 0.2 divided by the number of division between them, which is 10. So one small division is 0.02 amps. So if the needle is 2 division behind 0.6, that means 0.6 minus 0.04, and the reading would be 0.56 amps. Recording both the readings in the table, so 0.8 volts and 0.56 amps. Now the student rearranges the resistors between the terminal P and Q as shown in figure 3.4 to form circuit B and circuit C. The new values of V and I are shown in table 3.1. So in circuit B we have only connected R1 between P and Q, and in circuit C we are connecting R1 and R2 in series between the terminal P and Q, and we will note the respective value of V and I and record that in table. Second part says, for each circuit calculate and record in 3.1 a resistance R. Use the value of V and I in the table and the equation R equals to V divided by I. So to calculate resistance, we have to divide voltage and current. So for circuit A, the resistance would be 0.8 divided by 0.56, and the value of resistance is 1.43. Now for circuit B, I will divide 1.4 with 0.46, and the resistance would be 3.04. For circuit C, I will divide 1.8 with 0.29, and the resistance would be 6.21. Now calculate RA, use the value of R from circuit A and the equation given. R of circuit A that we have just calculated is 1.43, and I will put it into the equation to get RA, so it would be 2 times 1.43. The value of RA would be 2.86 ohms. Now record the resistance RB. RB is equal to the value of R from circuit B. That means RB is equals to R of circuit B. And the value of R for circuit B is 3.04. So the RB would also be 3.04 ohm. Calculate RC. Use the value of R from the circuit C and the equation given, which is RC is equals to R divided by 2. R from circuit C was 6.21 ohms. So I will put the value and it would be 6.21 divided by 2. RC is 3.11 ohms. Second part says a student suggests that RA, RB and RC should be equal. State whether your results support the suggestion. Justify your statement with reference to the values from your results. For two values to be equal, the percentage difference between them should be less than 10%. The values of RA, RB and RC are these. I will calculate the percentage difference between them by using formula maximum value minus minimum value divided by maximum value times 100. So the percentage difference between RA and RB can be calculated by maximum value, which is 3.04, minus minimum value between them, which is 2.86, divided by maximum value, which is again 3.04, times 100. Now the percentage difference turned out to be 5.92%. That means RB and RA are equal. I'll do the same for RB and RC, and the percentage difference is 2.25, and for RA and RC Again, the percentage difference between them turned out to be 8.04%. These all percentage differences are less than 10%. That means that these values are equal. And the justification is that all lie within the limits of experimental accuracy because the percentage differences between them is less than 10%. D part says the circuit used a 3-volt power supply. Briefly explain why resistor Rp shown in figure 3.1 must remain in place throughout the experiment. Rp has the resistance of 4 ohm. Use table 3.1 to support your answer. Rp has the resistance of 4 ohms and the power supply is 3 volt. If we remove Rp, then the combined resistance or the equivalent resistance of this complete circuit would be reduced. And because the resistance is reduced, the flow of current or the value of current in the circuit will increase. So Rp is necessary to maintain the current. That means the answer is Rp is limiting the current in the circuit. Without Rp, current value will exceed. E-path says a student determines the resistance of R1. He uses a variable resistor in circuit B to control the current and draws a graph of V against I. Part 1 says draw the circuit symbol for a variable resistor. A variable resistor symbol looks like this. Briefly explain one advantage of using a variable resistor to control the current. If you are using a variable resistor, you are not supposed to break the circuit every time and change the value of resistance to change the value of current. You can do it simply with one resistor. So we do not have to constantly change the resistors to change the value of current. Question number 4 says, a student investigates the refraction of light. Refraction is the change in direction of ray of light when passing into a transparent substance as shown in figure 4.1. So light is entering from one transparent medium into another, and when it enters the next transparent medium, it bends from its original path. Let's suppose this is the normal, which is at 90° at the interface of the two mediums. This is the angle of incidence and this is the angle of refraction. Question says, plan an experiment which enables him to investigate how the concentration of gel affects the angle at which the light is refracted when passing from air into the gel. A transparent gel block can be made by dissolving gel powder in hot water in a mold and allowing it to cool. Changing the amount of powder will change the concentration, and concentration is measured in gram per centimeter cube. So we are preparing a gel of different concentration C1, C2 and C3 by mixing different amount of powder into hot water, and we will see the respective angle of refraction for each amount of concentration. The apparatus available includes a sample of gel made at different concentration and label with those concentration, and a ray lamp which produces a narrow ray of light. In your plan, list any additional apparatus needed. Additional apparatus that we need is a meter ruler or a scale to trace the ray of light and a protector to measure the angle of refraction or incidence. Now we have to tell the investigation we are supposed to do. Firstly, we will prepare a gel of different concentrations. After it, we will shine the lamp on gel at specific angle of incidence and note the angle of refraction. After it, we will repeat this on all the gels of different concentration and note the refracted angle for each concentration while keeping the incidence angle same every time. For better results, we will take multiple readings for single experiment and then take average. After it, we are supposed to tell the variables that are constant. So the constant variable is angle of incidence of light. After it, we have to draw a table. So on the first column of table, we will write the concentrations and then angle of incidence. That would be same for every time, and then angle of refraction for each amount of concentration. Lastly, we will draw conclusion by drawing a graph of concentration on x-axis and angle of refraction on y-axis, and then comparing our results. Thanks for watching the video. If it was helpful, please hit the like button and subscribe my channel.